Hey everybody, it's Ken's Talk here. Thinking about one of the most important puzzles that all of humanity has ever contemplated, I guess, which is programming human life. Is it possible? What you're looking at on the screen right here is the beginning of chromosome 1 of a mapped genome that Craig Ventner and the whole crew did back in the early 2000s. Shotgun sequence, DNA sequencing. I'm going to be talking a lot of terms that if you're not familiar with DNA base pairs, you think you're not going to know what the hell I'm talking about. So hopefully we'll try to dumb it down as much as we can. I am not a geneticist. I have no background in this. I know Excel, and and that's all I know. But I enjoy organizing data and figuring out puzzles. And word on the street has it, that DNA has an order. There's 3.2 billion base pairs or nucleotides in like half of the genome, really, of Homo sapiens, of humans. And there are patterns, and these things code proteins, which make the physical structures that compose the sacs that are our bodies, along with a lot of other things. And we are not going to change this. Now, it's very interesting. People, scientists, everybody, we're working on mapping the genome. We understand certain things, but a lot of what we know is by comparing what we see, sequencing genomes and then comparing what we see, and not necessarily creating or understanding from scratch what the order means. Well, I have some ideas for this, and I have exported a portion of chromosome 1. Here I only have 10,000, 10,000 base nucleotides here. The simple logic is T, which stands for thymine, always bonds with A, and C, which is cytosine. Thymine always bonds with adenine. C, cytosine, always bonds with guanine. So I only listed one base pair. I didn't list the one that it bonds to, even though they're pairs and they come in pairs, just to save space. So we've got 10,000 here. The actual chromosome, full chromosome 1, if I wanted to deduct the entire chromosome 1, it averages 249 million base pairs. Now, if you go to the bottom of Excel, in this type of Excel, you are going to hit about 1 million plus. Yeah, 1,048,000. So you're looking at about 250 sheets, or a little less, to be able to fit the entire chromosome in this type of order, which I'm going to pivot table and show you, because that's what I know and that's what I'm having fun with here. Now, so there's an economy of scale issue that I have not completely addressed, although I know there are solutions to it, and in the future processing speed and memory and all that stuff's all going to increase. So hitting that 3-point-some billion character limit will be possible probably in the near future, if it isn't possible already. So what does all that mean? What's the point of all this? Well, the human brain recognizes patterns, and my goodness, is this a list of things that seems like patterns. How would you table or organize all this information and see what it means and do comparisons on the fly between genomes and things like that? And here are my ideas, basically, right? I was messing around with this before, and the first thing I saw is this is supposedly the start of the genome. As you'll see, some of the genome is missing here. They didn't get 100% of it done. Bummer. But look at this. You got a T, you got an A, you got an A, you got a C, you got a C, you got a C, T, A, C, C, C. Uh-oh. That's look like a repeating. So let's write some logic to say every time we see this pattern of T, A, C, 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 we say, hey, that means something. That's something we were looking for, right? This is very easy to do in Excel. This thing, does this equal T? Yes. And what else? Does this one equal A? Yeah, okay, that's what we want, equal A. And then we want this one to equal A. And then we want this one to equal C. And I'm just simply, going down the line here. This one also needs to be C. Just have to put the letter in quotation marks, and you're good. And then this one's C. So if all this happens to be true, you're going to get the word true here. In this area. Now, as you go down, you get a false when it's not true, because this is an A. So this is not this pattern right here. When you click on the cell, you'll see that this formula now applies to this area, and that's not the exact pattern that we said, even though this area is part of this TAACCC pattern, right? But how many instances does this occur? Now, once you do that, you can then just take this formula and paste it all the way down, for your entire genome. Here you've only got 10,000, but theoretically you could dump this in the entire chromosome 1 and the whole 249 million sequence patterns. You'll get this formula. And something else that I did to save time was I shrunk this down in some data magnification. I said, we're going to put this in a table, so what we need to do is we need to be able to see smaller segments rather than just listing 10,000 rows. So all this is in a table, meaning you highlight this area and you go to Insert and Pivot Table, and I already did this over here. And let's refresh, let's see what happens here. I've got some structure set up to show what we're looking at. Now, the pattern that we were looking for, which I called the logic column, right here, we're looking to see when that is true and where that is true. And instead of, what we're looking at right here is the existence in the entire 10,000 characters or nucleotides of how many A's, how many C's, how many G's, how many T's were there. And N, which is really should be question mark, I think it means nucleotide because they weren't able to identify it in the sequencing process. This was an old sequence. I believe we've gotten better about sequencing almost the entire genome, if not the entire genome, but back when this data was gathered, we weren't. There's 1,978 of those. Bummer. Now, I'm going to start flipping this table around, and it's going to start showing different things. Let's go with the condensed version. This is every 1,000 characters of DNA. And I'm collapsing it. I'm collapsing all of this by every 10,000 things. And this count of sequence, you don't even have to pay attention to that right now. What I want to know is the logic part of this, which is how many times does that sequence, which we found over here, this TAACCC, we don't even know what it means yet, how often does it occur? And the answer is, well, let's open all these up and I'll tell you. It occurs a whole lot in the first 1,000. It occurs 67 out of a possible 432 times, or 67 plus 432. That's a lot. That's hitting their light. Keep in mind that you're getting a false in between. These are all false, but technically they're really true because this area of the genome is part of a pattern we have identified. Not so much here. There's no truths at all. Doesn't even come up. Nothing there. Why? I'll tell you why. I know why. Let's grab your base pairs. Let's see what's going on here. Now I've just moved all the bases to column labels. And what that does is it gives a different view of where the bases are within the genome. And I could really go on forever with this. I'm just doing a proof of concept to show you how cool it is because it is so ridiculously cool. I'm learning everything as I go along. We don't care about grand totals in this scheme. So why hasn't anyone done this? People have done this. Why haven't they done this in Excel before? Because Excel, up until a few years ago and even now, isn't big enough. There isn't enough processing speed to be able to handle all of this. And where is there enough processing speed, by the way? Supercomputers? Well, supercomputers are a dime a dozen, or not a dime a dozen, or $10 trillion a dozen. And they're not ubiquitous everywhere. We haven't reached that level of processing speed yet. So doing this kind of line-by-line, sequence-by-sequence comparison is really freaking difficult. Count of sequence, and then I'm going to bring the actual sequence number into this table as well. And what I'm doing is, and you probably can't see that because it's hidden, I'm going to move that, actually, move this table over so that you can see what I'm doing. So I'm just creating a hierarchy here. When you open this up, you find out exactly what sequences there are T's, right? And there are truths. 1, 7, 13, 19. There is a pattern here at the very beginning of chromosome 1. And notice all the N's here. This column with the N's, those are the unidentifieds. This chunk of the genome was not sequenced properly here on chromosome 1, so we don't know what's going on. And when you start to make this a chart or a graph and see how all this relates visually, then you can start to open up and really, really have an interesting time about everything. I mean, it's just so freaking awesome. I can't help myself. So my goal is to put my entire genome in here and then compare it to databases that exist online and start to figure out what all this means and play with the logic. False, 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 false. So this sequence, is that true? That there's no existence of TAAC No way. Really? This sequence right here only exists in the first 10,000 characters of DNA? Is that what we just figured out right now? Because you're getting no trues down here at all. Like I opened up all these areas. Here's another way to look at it. If we open up our field list and we say, give me the logic first and then the 10,000 next, it only happens there. That's it. It only happens in the first 1,000. Now let's do a little test to make sure that I'm not crazy. How about instead of TAACCC, let's get rid of the last two C's. I'm getting rid of the last two C's, and now I'm just saying we're looking for TAAC, right? So don't worry about this. We're going to go no fill on that. And we're going to take this formula here, and then we're going to paste this formula down. This is the beauty of Excel, is how quick it is to pivot on a dime and change your stuff. Now when we go back and refresh, I expect to see some truths that are, I mean, you think you're going to see that 4-character pattern somewhere else. And we open it up, and we see that, yes, that 4-character pattern also exists in the third 10,000, the fourth 10,000. It's very rare, though. It's very rare. And a couple times at the end. Man, I don't know. I'm getting excited. You're probably not a nerd like me, and you're not so excited. But what does all this mean? What? Could we take genomes that we sequence of ourselves and then take them a few months later or a few years later and do this line-by-line base pair comparison and figure out what the hell's going on? And the answer is, I think, yes. And that's what I want to do. So there's a proof of concept. You can watch for Ken's talk to be coding his own freaking genome and getting 3 billion characters in a table somehow through data magnification or through something else, and tabling this and graphing it and charting it and helping the cause, because I can't think of anything more interesting than decoding this biological puzzle and then hopefully synthetically generating DNA to do exactly what we want it to do, so that I grabbed a couple different files here online. For example, there's a bunch of studies that are going on here that are talking about different types of phenotypes or cancers or things like that, that they're doing genome sequencing of these diseases and cancers and finding out what they find, because we still don't really understand how the base pair, after it gets transcribed and starts creating proteins on the fundamental level, at the unique nucleotide level. I think we are still grasping at straws, because there's just so much information, and the computing power is only recently coming online to handle this. So there's your proof of concept. But have fun. I can't think of anything more interesting. I really can't. And if you're interested in following the progress, follow me on YouTube. Send me any questions. You want to know how I did this, or how I imported, because the data comes in 70 character strings in a cell. I wrote some formula to essentially transcribe it into this unique column of a base column right here. And then there's all these logics, and then there's all these other things. I'm going to build out. I'm going to put molecular weights in here. I'm going to put. I have a periodic table of elements sprap as well. Sprap is what I call these crazy Excel things. And in that periodic table of elements, you see, like, when you look at the chemical makeup of these base pairs, there's a lot of nitrogen, there's hydrogen, there's some oxygen, there's carbon a little bit. And to figure out, like, these adenine and guanine are the biggies. These are actually bigger base pairs than the other two, and that matters. Like, you can write a formula here and say which one's big and which one's small, and then put that in the table, and it's never going to end, because it's enormous, and it's a puzzle that is worth solving. So that is the story. That's the proof of concept. Let me know if you're interested, because I do nothing but mess around in Excel all day, and this seems like a lot of fun. So that's it. Ken's Talk out.